In this Coulombs Law example, we have three charges in a straight line. On the left, we have a positive 3.3 times 10 to the negative fifth Coulomb charge. In the middle, we have a positive 2.1 times 10 to the negative fifth Coulomb charge. And on the right, we have a negative 6.7 times 10 to the negative fifth Coulomb charge. And you can see the distances between them from the center of the charge to the center of the next charge. What we're going to do here is we're going to look at the individual pairs. So I'm going to call this charge A, this charge B, this charge C. And I'm going to look at the different pairs. So we have three different pairs. We have the force that exists between charges A and B. So we ignore C for now. We're going to just kind of pretend it's not there, and we're just going to look at the the force that exists between charges A and B. So again, we just use Coulomb's law. So 9 times 10 to the 9th times 3.3 times 10 to the negative fifth, that's the charge on number 1, and then 2.1 times 10 to the negative fifth, that's the charge on number 2, basically A and B. Again, you don't worry about the positive signs and the negative signs. You worry about that later on. And we divide that by the distance between the two of them, which is 0.1 meters, and we square that. And so what we end up with here is, if we calculate this out, it's 623.7 newtons. So I'm just going to leave that for now. I'm not going to worry about that. I'm going to come back to that later on. We're going to look at the next pair then. So we're going to look at the force between B and C. So it's a very similar calculation. So we have 9 times 10 to the 9th, that's our constant, times 2.1 times 10 to the negative fifth, times 6.7 times 10 to the negative fifth, so the charge on B, the charge on C, since we're looking at those pairs right there, B and C. And we divide that by the distance between the two of them, so that's 0.15 meters squared. And if we multiply that out, we get 562.8 newtons. And then we're going to look at the last pair that we have, and that's between A and C. So the force between A and C. Very similar again, 9 times 10 to the 9th times 3.3 times 10 to the negative fifth times 6.7 times 10 to the negative fifth. Now the distance between them, instead of being 0.1 or 0.15, from A to C, it's a total distance of 0.25. I just add the distances together. So 0.1 plus 0.15 is 0.25. So I know this is 0.25 meters squared. And when I multiply this out, I get 318.384 newtons. So the question then now is, what does that mean? Well, what we did is we basically found the different force pairs that we have on A, B, and C. So if we draw these out again, I'm just going to draw this over here on the right. So here's A, here's B, and here's C. So those are the three that we have. If I just draw in what I have here in terms of forces, between A and B we have a force of 623.7 newtons. This is where we have to take the positive and the negative into account. So we have a positive charge on A, a positive charge on B. So we have a repelling force between the two of them, which means A wants to move away from B, B wants to move away from A. So the force is pushing them apart. So on A, I know I have this 623.7 Newton force to the left. On B, I have this 623.7 Newton force to the right. Then if I look at B and C, I have this 562.8 Newton force. But B is a positive charge, C is a negative charge, so they're attracted to each other. So B has a force towards C, C has a force towards B. So I'm going to draw them in the directions towards each other. So on B, we have a 562.8 Newton force to the right. On C, we have our 562.8 Newton force to the left. So that's towards each other. And then the last pair we have is A and C. So between A and C, we have a force of 318.384 newtons. Again, positive, negative, they're attracting each other. So A has a force to the right, C has a force to the left. So the force on A due to C is 318.384 newtons to the right, and then C is 318.384 newtons to the left. So what I typically would ask you for a question like this is, what's the net force on one of those charges? So I might ask you, what's the net force on A, what's the net force on B, what's the net force on C? So all we have to do is basically just look at our vectors, just like we've done in the past, and find our net result. So on A, we have 623.7 newtons to the left, we have 318.384 newtons to the right. So they're opposite directions, we have to subtract them. So if I take 623.7 minus 318.384, I get a net force of 305.316 newtons to the left, because there's more force to the left. On B, we have two forces to the right, so I'm going to add them together. So if I add 623.7 plus 562.8, I get a net force of 1,186.5 newtons to the right. Draw the arrow below there so I have a little more room. And then finally on C, they're both to the left, so I'm going to add those together as well. So we have our 562.8 newtons, plus we have our 318.384 newtons, and so that adds up to be 881.184 newtons to the left. So that's really what we're talking about using Coulombs law, and that's how we can find our net forces on each individual charge when you have more than two charges present.